Let's look at part two of lines and planes in space. Two distinct planes in three space are either parallel or intersect in a line. For two planes that intersect, the angle between them, and it'll be an angle from 0 to pi over 2, we'll always look at the acute version, from the angle between their normal vectors, so N1 is going to be the normal vector from plane 1, and N2 will be the normal vector from plane 2. As a reminder, a normal vector, think of a plane as a sheet of paper laying flat on your desktop or tabletop. And then if you stand a pen or pencil up on that sheet of paper, that pencil or pen is your normal vector. The sheet of paper is your plane. This formula, cosine of theta, equals the dot product, and the absolute value of your dot product of your normal vectors will be your numerator, and divided by the magnitude of each normal vector multiplied together. It's very familiar with your angles between vectors, but this was angles between planes. Let's make a note that if N1 and N2's dot product is 0, then you have two planes that are perpendicular to one another. They're parallel to one another. It would be like two sheets of paper that never intersect. That's if one of your normal vectors is a scalar multiple of the other. Example, let's find the angle between the two planes. The first one is x minus 2y plus z equals 0. The second plane, 2x plus 3y minus 2z equals 0. We're going to find the angle between, and then we're going to find parametric equations of their line of intersection. So first, let's take the coefficients of x, y, and z. That's going to be the values for your first normal vector, and then the coefficients from the second plane will be the values for your second normal vector. To get the angle between, we're going to follow this formula. N1 dotted with N2, 1 times 2 plus negative 2 times 3 plus 1 times negative 2. So that's 2 minus 6 minus 2, which is negative 6, and its absolute value is positive 6. Underneath, the magnitude of N1 is the square root of 1 squared plus negative 2 squared plus 1 squared. Well, that's 6, so square root of 6 is the magnitude of N1. Repeat that for N2, the square root of 2 squared plus 3 squared plus negative 2 squared. That's 4 plus 9 plus another 4, that's 17. 6 times 17 is 102. So 6 divided by square root of 102, and you'll want to keep at least 4 decimal places to maintain accuracy. Cosine inverse of this decimal is about 53.5 degrees. So that's the angle between the two planes. If you had two sheets of paper that intersected one another, then the acute angle at the intersection would be 53.5 degrees, roughly. Okay, now, to get the parametric equations for their line of intersection, we're actually just going to physically set each plane equal to one another. So plane 1, plane 2, and we're going to solve that system of equations. Now I'm going to use the process of elimination, where I'm going to take the top equation and I'm going to multiply every term by negative 2. So negative 2x plus 4y minus 2z equals 0. When I add, the x's drop out, so I get 7y minus 4z equals 0. Isolating for y, you would add 4z and then divide by 7. So y is equal to 4/7 z. From our first equation, and that's the first plane. You can pick either plane because this is where they intersect, but I'm going to choose this first plane because it just looks easier to work with. So I've got x minus 2y, but this y I'm going to replace with 4/7 z, so it's minus 2, used to be y, now it's replaced, plus z. And that tells us that x, if you solve it out, this is negative 8/7 z plus 7/7 z is negative 1/7 z. But when you carry it over and solve for x, you get a positive 1/7 z. I'm going to let t be z over 7, and so x is equal to t. For the y value, we already have z over 7, so it'll be 4t. And when you solve for z, z is going to be 7t. Multiply both sides by 7. The direction numbers a, b, and c can also be found by using the cross product of your normal vectors. Remember, top row is ijk, the values from n1, the values from n2, and those were taken right off of the coefficients for the planes. So remember back those two equations that were the two planes that we're finding the intersection of? These were the coefficients for x, y, z. And that was plane 1, plane 2. So we've done this quite a bit, cross product. So you take the determinant times I minus the determinant j plus the determinant k. Positive, negative, positive. Always remember to rotate those signs out. All right, so we've got 4 minus 3, that's 1i, minus negative 2 minus 2 is negative 4. Negative 4 is positive 4. That's for the j. And then 3 minus negative 4 is 7k. Theorem, the distance a plane and a point, the distance between a plane and a point Q not in the plane is given by the magnitude of the projection of PQ onto N, which can also be calculated as the absolute value of the dot product from PQ and N over the magnitude of N, where P is a point in the plane and N is normal to the plane. Example, find the distance between the point Q, 1, 5, negative 4, and the plane 3x minus y plus 2z equals 6. Okay, so recall, if you know the equation of the plane, you can take x, y, and z's coefficients, and that gives you your normal vector to the plane. Now, we need a point in the plane, and in order to do that, we don't use Q right off the bat. We need a point on the plane, so it's very easy to calculate, and try to make it life easy on yourself. If we start with this plane, because we need a point in the plane, you can actually let two of the three variables be 0. So I'm going to choose to let I'm going to choose to let y and z both be 0. If we let y and z both be 0, then all that's left is 3x equals 6. Well, 3x is equal to 6 when x is 2. So that tells us the point in the plane, we used the plane equation. We found x to be 2 when y and z were both 0. Okay, so now we've got a point in the plane, some other point that's not in the plane, and we know a normal vector to the plane, just taking it from the coefficients. All right, so remember, your directed line segment is terminal minus initial, 1 minus 2, negative 1. 5 minus 0, that's 5. Negative 4 minus 0 is negative 4. Now that we've got the directed line segment from a point in the plane to a point not on the plane, we're going to carry through with our distance formula. PQ dotted with N, so that's negative 1 times 3 plus 5 times negative 1 plus negative 4 times 2. That all works out to 16 once you take the absolute value. That's our numerator. The magnitude of our normal vector to the plane is square root of 3 squared plus negative 1 squared plus 2 squared, and that totals out to 14. So 16 over square root of 14 is about 4.28 units. That's the distance from that point to this plane. An alternative distance formula between a point and the plane can be calculated this way. Now, remember, Q is a point not on the plane, and a normal vector to a plane is represented by the coefficients of x, y, z. So what you want to do in this alternate distance formula is you take the entire plane, make sure everything is on one side and that the plane is equal to 0. So your constant will be on this side instead of the right side. Gather all your terms in order and your constant, make sure it's equal 0. Then the coefficients in your plane's equation, A, B, C, and D, those 4 numerical values, A will be multiplied with the x value from Q, B will be multiplied with the y value from Q, and C will be multiplied with the z value from your point. This numerical value of D will just remain the same. Take the absolute value of all that, and then this is still the magnitude of your normal vector. So let's check this out. Another example. 2 parallel planes. Now notice, if you multiply this equation by 2, you get exactly the second one. So we're going to find the distance between 2 planes. First, choose a point in the first plane. Again, it's very easy to let two of your three variables be equal to 0. If we let y and z both be 0, then that takes us down to 3x minus 6 equals 0. So x is 2, giving us the point 2, 0, 0. X equals 2 when both y and z are 0. From the second plane, we can just steal those coefficients, 6, negative 2, 4, and 4. All right, so kind of see what we're doing here is we're leaving one plane as is. We're taking a point from the other plane, and now we'll apply this formula. All right, so we've got a point from the first plane, the numerical values from the equation of the second plane. So it's a times x sub 0, 6 times 2, plus negative 2 times 0, plus 4 times 0, plus 4. That all fits in here. Just make sure you're careful to line up your A's, B's, C's, and all that, because there's quite a few in the formula. We're going to get 16 again, and then if you take the normal vector of the plane, the second one specifically, 6, negative 2, 4, square each one, add them up, square root, you get square root of 56. And so the distance between these two planes is a little bit more than 2 units. Theorem: the distance between a point Q and a line in space is given by the magnitude of the cross product divided by the magnitude of u. U is a direction vector for the line, and remember, direction vector is the one that is parallel or points in the same direction as PQ. That was from the very first slide. And P is a point on the line. So let's do an example of that. Find the distance between the point Q and the line given by these parametric equations. Okay, your direction numbers are the coefficients of t from the parametric equations. So vector u, the direction vector, is 3, -2, and 4. If we let t be 0, then that gives us, and you can let t be any number as long as it's uniform across the board. 0 is easy to use because it eliminates terms. So x is -2. If t is 0, y is 0. And if t is 0, z is 1. It's just easy to get a point on that line. T equals 0 is very convenient. All right, so we have a direction vector and a point. Our directed line segment PQ, remember it's terminal minus initial. So 3 minus -2, that's 5. -1 minus 0, and 4 minus 1. Now that we have a directed line segment and a direction vector, we can do the cross product. Remember, this is ultimately the formula we're after. So we had to build a point for PQ. U came straight out of the parametric equations, specifically the coefficients of t. Now let's do the cross product. So we have ijk. We're going to put in our values from PQ, 5, -1, 3, and our values from U, 3, -2, 4. Carrying out the cross product, we get 2i minus 11j minus 7k. We can write that as 2, -11, and -7. Okay, so here's our cross product. Remember, magnitude is each one squared and added together under a square root radical. So I take each of these numbers, square them up, 4, 121, 49. That makes square root of 174. For u, 3 squared plus -2 squared plus 4 squared, that totals out to 29. 174 divided by 29 gives us square root of 6, which is almost 2.5 units. I hope this video helps. I want to do it in a second part just because the material is so long in the lines and planes in space. So this is part 2. If you have any questions, reach out, email, phone, office hours. I'll do my best to help you out.